Welcome back. This is Eric, and we're going through part 2C. We're going to finish up question 2 here. So we've found our boundary conditions with regards to x, and I've deleted that out for clarity, and we've applied those to figure out how to solve for particular solutions in terms of our separation of variables. And now what we're going to do is we're going to find the corresponding time solutions. So we're going to look at case 1 to start with, which was our constant solution, which came from the linear solutions. So this is dealing with this case, case 1. We've eliminated that case, so we don't have to worry about it. And this just gives us that the time function is a constant. So we know for x of x is equal to b, which satisfies the boundary conditions, that for the product, which gives us our separation of variables, u of x of t type solution for this particular case, we get b times e, which is just a constant. So likewise, for case 2, we get x of x is equal to this a cosine kx plus b sine kx, but b is equal to 0 and k is equal to n pi satisfies the boundary conditions. So for this case 2, we now have a time component that does vary in time. So this is some coefficient e times d k squared t. So for the periodic aspects here, going up to higher k loops us around and produces finer features. In terms of time, it means that things are going to go faster. So this gives us, and here I'm just writing out, just copying e times e to the negative k squared dt. Let's just double check that that's right. Yep. Okay. And so let's find this product of x of x, t of t. We know that that term goes away, so we've just got a cosine. Then I'm going to substitute in n pi x for k. And then we've got e to the negative pi n quantity squared dt. So and we can simplify that out by noting that a is a scalar constant and e is a scalar constant of some sort. And so if we want to get our general solution u of x of t, we've got some constant value a naught plus a sum over all these integers, keeping in mind that n is equal to 1, 2, 3, 4, ... of a sub n cosine, oops, can't use the k, gotta write in n pi x, and then we've got e to the negative pi squared n squared dt. So we've got our time portion and we've got our spatial portion, and we've got a sub n's, and these might be used to satisfy some initial conditions. Let's write that correctly. Used to satisfy ICs if provided. So we don't have a unique solution here. We have a general solution that satisfies all of our boundary conditions. Now, an astute student might notice this particular term means that we can find these things in terms of a Fourier series. So if, for instance, if you were given initial conditions with regards to, say, t is equal to 0, then this term might go to 1, and then you're just looking at matching your a sub n's and your a sub zeros in terms of using the Fourier series technique. That is very explicitly not part of this problem, but it's a good thing to be aware of. All right, and that's question 2.